So the second presentation is on gabion retaining walls. So again, it's a very popular type of retaining wall. Like it's what we call an externally stabilized system. That means we are supporting the soil from the outside. So it's like one type of mass gravity retaining wall, like PCC, masonry. Similar to that, we use the gabion retaining wall. So main thing is the gabion mesh. So first, this is manufactured from steel wire. So we can buy the wire, then put into the machine, then we make the mesh, which is typically maybe around a meter width. And the mesh can be again into rolls like that. And we call it hexagonally woven double twisted wire mesh. Hexagonal means the aperture shape is like a hexagon. Then double twisted, like you can see the wire is twisted twice actually. Like sometimes people call it double twisted, triple twisted also, but it's main thing. Like we can compare with this that normal chain link mesh, like we use for this fencing and all. So here we can see this is only one kink actually. So here, if the wire gets cut or broken, then the entire that mesh unravels like that. But here it doesn't happen. Like even if it is cut, it remains stable. So that is the advantages of the double twist. Then in a mesh we have different, like one is along the borders, like the edges of the mesh, like we have the selvage wire, which has to be slightly stronger. Then the main mesh, the mesh wire we call it. Then another is like the gabion is like a box, like so the bottom and the vertical, it is joined by a lacing wire, like that, by lacing. So we have three types. Like this is the lacing wire, we can see this is like two meshes which are being joined by the lacing wire. Then if you look at the specifications, like there is the core, which is a steel wire. Then it is galvanized. That means we provide a coating of zinc to protect it from corrosion. Over that, we may or may not have a PVC coating. Like, see, normal situations, we go for just a galvanized gabion. But if it is exposed to a lot of water, probability of corrosion, we both zinc and PVC coated. So if you look at the wire diameter, like mesh wire is 2 to 4 mm typically. Then selvage wire is 2.4 to 4.4 because it is the border, it has to be slightly stronger. The lacing wire is 2.2 to 2.4. Then zinc coating thickness, it's like 200 to 300 grams per meter square. PVC coating thickness is typically 0.5 mm thickness, like that. So again, now they have more like coatings which are better than zinc, like aluminum or some different combinations are there, like that. Then again, mesh size is another criteria. Like we have these, like we have 60 by 80 mm, 80 by 100, 100 by 120, like that. So normally, if our stones are smaller, because gabions have to be filled with stones, if the stones are smaller, we have to use a smaller mesh size. Then it is actually pre-assembled in the factory. Like so, each piece is separate, like cut. Then here, like they do the lacing. Like this will be laced, bottom will be laced. Here also. Then and again, see normally there is internal partition. Like suppose this length is 2 meter, but we'll have a one partition in between. This is also laced. Then this will be folded like this. Again, folded, folded. Everything can be folded and in a collapse form, like then it can be sent to the site. So this type of bundle, it will be dispatched to the site. Then the site, what they do, they just make it into a box. So now again, these are all assembled in the factory like that. This lacing was done. See now I just put it and here I'll have to do the lacing at site like that. All this here. Then finally, the lid has to be closed, filled and lid has to be closed like that. So this is the assembling at site. Now the lacing also, the specifications are given, like there is a double loop and what is the spacing at which it has to be done. Normally the construction or installation guidelines will give that. Now the stone for filling, see normally we need like hard angular stone. Like sometimes what happens if we go to hilly areas, we get a lot of rounded boulders. These are used, but we know like rounded boulders, like interlocking is very less actually. And this gabion itself is a flexible, like if I put just imagine very spherical thing, it will easily bulge out actually. So normally ideally is angular stones. Then size also like well graded between 100 to 200 mm. Like see normally the gabion cell may be like 1 meter by 1 meter by 1 meter. So I cannot put just 1 or 2 stones in that because again the strength comes from interlocking like that. So there is a maximum size. Then the minimum size it should not escape through the aperture like that. So there is a minimum size of stone, maximum size of stone. Then filling, there is a sequence actually, like see normally what happens. So suppose this is the height difference between adjacent cells should not be too much again, because again this mesh is a very flexible. So if I fill this to the full height first and keep this empty, then it will bulge out actually. So there is a proper sequence, it has to be done like that, so that all the cells are filled in a sequence. Then filling of gabion, like one is the stone of appropriate size and well graded like that. So probably when we have a well graded, there is very good interlocking between different sizes. So that gives strength. Proper sequence of filling. Then all exposed faces to be carefully hand packed. Like exposed face, so there we have to pack the stones carefully. Like that means, like if one way I can take a JCB and just dump into the gabion, so there the stones will not interlock. So probably the interior part I can do that, but at least the outer exposed face, there I have to do proper hand placement. Otherwise what happen? My gabion mesh will bulge. The inner part, see both it will balance. Like. Then another is proper cross bracing at 1/3 and 2/3 height. Like see here what happens, like many places you can see like gabion walls somewhere along the road you can see somewhere it can be bulged out. So mainly because of at this here you'll have to properly hand place actually. Because this mesh itself, like if you dump very loose stones, the mesh is a very flexible mesh. So you cannot just confine, so it will just bulge out actually. So proper packing of stone is very important. So here, probably we can see it's well placed. And normally there is actually cross bracing actually. Like suppose it is a 1 meter, normally at 1/3 height, again with the lacing wire, the opposite side has to be, we have to give bracing. Otherwise what will, to prevent the bulging. 1/3 height and 2/3 height, it has to be done. So now we can have different configurations. Basically what we do, we just go on stacking the gabions to make a retaining wall. So one is like the flush face, this is the exposed face, like it is flush. Like, so here it is staggered like that. So normally like any gravity wall, we need less width at the top, maximum width at the bottom, like so, staggered. Then flush face with inclined base. See normally what happens, the pressure tries to push the gabion forward. So it has to be resisted by the friction at this face. So one way of increasing sliding resistance is to make it slightly inclined. So this will increase the sliding resistance. So normally like 6 degrees is commonly used. Then another is nominal setback. See again, if I keep it perfectly vertical, one thing is stresses are more at the face. Similarly, like there are placement errors, slight bulging, it may tilt outward like that. To prevent that, always like any retaining wall, we can see even like a RCC cantilever wall, the stem is not exactly vertical, it will be slightly, like if you look at the Bowles book, like says I think 1 in 48, like the stem has to be. So mainly this is for aesthetic reasons also, like if it's a tall wall, if it is made perfectly vertical, when you're standing there, it looks unsafe actually. But if it is slightly inside, like psychologically, it is more. So normally here the setback is like one mesh we can set back like that. Either we can make it horizontal base or inclined base. Then this is with setback. See, basically as we go up, we have to go on reducing the width actually. One way is with the like setback. That means suppose this is 3-meter gabion. Next layer I use a 2-meter width gabion. So half a meter like that. Again, there is a limit, like the setback cannot be more than the half of the height actually. Like. Then again, we can have this is back faces flush and front setback with inclination. Here we have the other way, like the front is flush, back is step back, again with inclination like that. So these are like various combinations are possible. See now, coming to the design, like so basically gabions are a simple form of gravity retaining wall. So the design procedure is exactly same as for a like a PCC or masonry wall. So only the here one idealization we do is like, so normally this is a stepped configuration. So we assume what is known as a virtual back of the wall. That means we join this point to this point. So we assume this is the virtual back like that. Similarly, it can be done here also. Then the top width is there, bottom width is there, height. Then we should know the backfill properties, like typically C dash is taken as 0, as I mentioned yesterday. The friction angle or the angle of shear resistance of the backfill, then the unit weight. So for design, we use this like actual configuration, this step one, but design, we can use this idealized one. Then the another parameter is the unit weight of the stone infill. So again, it depends on the porosity and which type of rock, whether it is granite or basalt. So typically it is maybe something like 15 to 16 kilonewton per m3. So once you know the type of stone we are using, and normally I think we take around 40% porosity. So we can also calculate, assume 40% porosity, we can take the specific gravity of the rock, we can calculate the unit weight. Then we use the Coulomb's earth pressure formula. Like we know, like once we have defined this virtual back of the wall, this is the perpendicular, then I can assume the delta, angle of wall friction. Then I know my earth pressure will be at an angle delta to this. With this, I can calculate either resolve to horizontal vertical component, then do all the analysis. So here I have shown it horizontal, but actually in most practical, it will be slightly tilted, inclined. Then design calculations like check for sliding, overturning, eccentricity, like safe bearing capacity, then again global stability, check for settlement. Exactly same as for a gravity retaining wall. See now, like first, like we assume like the top width, we assume a bottom width. So normally from experience we know like what should be the reasonably. Then do all this check. Like if it is factor safety is achieved, well and good. Otherwise, we can go on changing the dimensions. See now, like we can do it like see overturning, like this each layer can overturn, like this block can overturn or slide. Similarly, this can also overturn and slide like that. So we can check for that. Or like if you have kept the setback within reasonable, like once you find you have done this overall stability, each part also, that also you'll find it will be stable like that. But we can always, to doubly ensure, we can check for that, like each. Then like we have no something known as internal stability, like for the strength of the gabion mesh, like we are not checking that. See, actually it's just a confining, like it's not really taking the load. And here only, like important is proper filling of the stone. That's very important. Like, otherwise that mesh will bulge out. Now coming to the advantages, like one is flexibility, because it's just a mesh filled with stone. We can accommodate a lot of differential settlement like that. Then it is very permeable, because stone, we are putting large stones, which is very porous. So it is very permeable type of wall. Then no need of machinery, like if it is a hilly area, like at a restricted space, like it's all is done manually, like the mesh, assembling the gabion, filling, all can be done manually. But sometimes like large works we can do with like machines also filling. Then one important thing is like the sustainability. Like the gabions can be reused, like stone, like even probably the gabion box itself, like if we remove the stones carefully, even the gabion box itself can be reused. So sustainability is one of the major advantages. Then coming to the drawbacks, like one is like it can be labor intensive because filling, that fabrication, like it's can be labor intensive, slow. Then poor construction may lead to bulging, like sometimes if the filling is not done properly, like stones are not unpacked, then the diagonal bracing sometimes it's not done, then corrosion is a problem actually. Like sometimes like we have that galvanization, we have PVC coating, but still sometimes you can find corrosion, especially in the aggressive environments. Then normally any gravity wall, so normally it's economical for small heights only, say 3 meters, 4 meters, not beyond that actually. But sometimes I find once I saw a like a project report somewhere in the hill road, like 15, 20-meter height gabion walls, like, so that is, I don't know, like no logic in that. Then economical wear, sorry, like this is good if stones are available locally, cheap like that. But if the stones are expensive, then this also becomes an expensive solution. Okay, I think with that I conclude, because design is very simple. Like basically, it's a gravity wall, so that's all. Like nothing very complicated there. Main thing is proper construction.